Algebra 2 students. Today's lesson is going to discuss solving systems of equations, just like we've done in previous lessons, but this lesson is going to involve having three variables. Now, just like we talked about in previous lessons, if we had two unknowns or two variables in equations, we needed to have at least two equations to solve. So when we're solving systems of equations with three variables, we are going to need three equations to find those variables. Okay, so when we do that, now we're introducing that third variable. And if you see in this picture here on the screen, it's showing you what three variables represented on a graph would look like. Instead of getting a line, which gives me that linear data with two variables, what we're actually getting is a plane, because as soon as I introduce that third variable, now we're no longer linear. Now we're representing from geometry that plane. So you can see here that orangish apricot color graph would be one equation, the yellow graph would be two equations, and the second equation, and the green graph would be the third equation. So what we're looking for is that one particular place, that one ordered triple value that finds the intersection of all three planes. Now, when I introduce that third variable, I have different scenarios that I could have when I'm looking for my solutions. So those intersections can be intersecting so that they intersect in exactly one point. Now, this is really what we're looking for. We're looking for that one value that gives me a unique value for X, for Y, for Z. All right, but when we're talking about planes, not all planes are going to intersect in exactly one place. They may intersect so that they're all intersecting on a line. So that means any of those values that fall on that line could represent solutions. So if all of the intersecting planes are intersecting in an exact line, we would have a scenario where we would have infinite solutions. And that would be the same as if they were the same line when we talked about linear graphs. All right, we also have multiple ways we could get no solutions. So you might see that we have more no solutions in this set than we've had in the past. So one of the ways is that the planes are all intersecting, however, not all three planes are intersecting in the same place. So here's the green and the white are intersecting here. The green and the blue are back here, and the blue and the white are over here. That would give me a scenario where I would have no solution. Or maybe two of the planes are parallel and they are intersecting the third plane, but again, they're intersecting in two different places. So that would show up as a no solution. And the last scenario would be that all three planes are just parallel to each other, meaning that none of them are ever going to intersect. In that scenario, again, we would have no solution. All right, so what we're trying to find here is we are trying to find a solution, but you're going to find scenarios where we're not always going to be able to do that because that one solution doesn't exist. All right, so let's look at our first example, just a generic example with three equations, and we are looking for X, Y, and Z. You'll notice that I started off with three separate equations. Now, I like to number those because it keeps my work a little organized and I know which equations I worked with already. All right, now what I'm going to do is I need to have a good sense of elimination because I'm going to work with two equations at the same time and I'm going to eliminate one of the variables. All right, so I'm going to choose first to work with equation 1 and equation 2. So what I'm going to do is I'm going to come down here and I'm going to look at these two equations and I'm going to go after getting rid of the z's. All right, so in order to get rid of the z's, looking at equations 1 and 2, I'm going to have to multiply equation 2 by 2. So that's going to give me 4x plus 2y minus 2z equals 10. And my first equation is going to stay exactly the same. So I'm not going to be solving anything here. I'm just eliminating my z's from the first two equations. So when I do a quick addition, I get 9x plus 5y. My z's cancel to give me a total of 12. Now I am going to put this equation here on pause, but I'm going to give it a letter just so I keep everything organized, and I'm going to call this equation A because I built that one. All right, now I can't use equations 1 and 2 together again. I can either use 1 and 3 or I can use 2 and 3. Now my goal here is to also get rid of z's again, so then I'll have two equations with just x's and y's in. So the second time what I'm going to use is I'm going to choose 2 and 3. Again, I could also use 1 and 3, it doesn't matter. Now if I'm trying to get rid of z's again, then what I'm going to have to do is I'm going to have to multiply the second equation by 2 this time. Same thing as I did in the last. So that's going to once again give me 4x plus 2y minus 2z is equal to 10. Now I'm going to leave equation 3 exactly how it looks. Then I'm going to add these two equations together, and that's going to result in 5x plus 6y. My z's are going to cancel, and I'm going to be left with 26 on the right side. I'm going to call this equation B. All right, now that I've built equation A and equation B, you can see they now have both x's and y's. So I'm actually going to start this problem over again, but I'm going to look at just A and B and what I need to do with A and B to get rid of either x or y's. So I'm going to go after y's. I say I have a 5y and a 6y, so I know the common multiple would give me 30. So I'm going to multiply my A equation by 6, giving me 54x plus 30y is equal to 72. I'm going to multiply my B equation by negative 5, and that's going to give me negative 25x minus 30y is equal to negative 130. So I just multiplied both of these, this A by 6 and B by negative 5. When I do that, I see that my y's are going to cancel, and I'm finally down to one equation with one variable. I'm going to be left with 29x is equal to negative 58. I'm going to divide both sides by 29, and that's going to leave me with one variable, x, which is equal to a negative 2. All right, now I only have found so far one variable, but now the other two are going to be pretty easy to find. Now I'm going to go back to where I built my x and y equations and either use A or B. So I can substitute that negative 2 in for x into either one of those equations. It doesn't matter. I'm going to use equation B. I'm going to make that 5 times negative 2 plus 6y is equal to 26. That gives me negative 10 plus 6y equals 26. 6y, take that 10 to the other side, gives me 36, and y is equal to 6. So now I found x and I found y. Now I'm going to go back up to one of the original equations. Again, I could use all three, It does not matter. I'm going to substitute my x, I'm going to substitute my y, and I'm going to solve for z. So I'm going to go ahead and plug this into the third equation, and that's going to give me -2 plus 4 times 6 plus 2z equals 16. And that's going to give me -2 plus 24 plus 2z equals 16. These two combined give me 22 plus 2z equals 16. I'll take that 22 over, and that's going to give me a -6. And I'm going to come up here and I'll have z is equal to -3. That's my third variable. All right, so if I put this as an ordered, it's no longer a pair, I'll call it an ordered triple. That'll give me x, y, and z. Now, what's nice about these, we can plug all of them back into the 3 original and do a quick check to make sure those 3 x, y, and z values work in all 3 equations. So it is a little bit of a process, but if you keep your work nice and neat and organized, it will be a little bit easier to accomplish. All right, let's look at example 2. So right away, I'm going to go ahead and look at these and label them 1, 2, and 3. So I'm going to try to analyze to see what's the easiest for me to get rid of. So I'm going to work on getting rid of y's this time. And in getting rid of y's, I'm going to start with equation 1 and equation 2. So if my goal is to get rid of y's with 1 and 2, I'm going to have to multiply equation 1 by -2. So that's going to give me a -4x minus 2y plus 6z is equal to -10. And I'm going to leave equation 2 exactly the same. You can see what I'm trying to do is get those opposite coefficients so that I can add and my y's disappear. So I'll add, and that gives me -3x. My y's are eliminated, plus 2z equals -3. Now there's that equation I'm going to call A. That's the one that I built. Now I'm going to go back to the original and I'm going to decide, do I want to use 2 and 3? Do I want to use 1 and 3? Now I'm still trying to get rid of y, so you have to get rid of the same variables the second time too. So I'm going to use 1 and 3. And if I'm going to get rid of y's, I'm going to need to multiply number 1 times -3. So that's going to give me a -6x, a -3y, a plus 9z equals -15. And then when I multiply number 3, well, I don't need to multiply number 3. I'm going to use number 3 as is. What I notice here is that things start canceling, giving me a 0. Now, on the right-hand side, I also get a 0. So that means that 1 and 3 were the same plane when everything cancels like that. And as long as the same plane is intersecting in a line, which that's what we have here, a line, that means that they're intersecting at the same place. So in this case, I'm going to end up with infinite solutions. Basically, anything that would fall on this line would be a solution to these 3 equations. Now, if I ended up over here with 0 is equal to 5, that means those are different planes. That means that they're going to end up being no solution. Okay, let's move on to our third example. Again, if I'm going a little fast, don't feel bad about pausing the video or rewinding to make sure you understand exactly what's going on. All right, let's look at example 3. I'm going to go ahead and number my equations. This time I'm going to get rid of x's first because I see that 3, 6, and 9 are all multiples, so that might be easier for me to find. So I'm going to take equation 1 and 2, and I'm going to get rid of x's, which means that I've got to multiply equation 1 times negative 2. That's going to give me negative 6x, positive 2y, positive 4z equals negative 8. I'm going to leave equation 2 the same, no change needed, and I'm going to add those together. So you can see that my x's are canceling out. I have 6y plus 12z equals 11 minus 8 is going to be 3. And this is going to be equation A. All right, now I'm going to look at 1 and 3 and try to get rid of x's again. So to get rid of x's, I'm going to have to multiply 1 by negative 3, giving me negative 9x plus 3y plus 6z equals negative 12. And I'm going to leave the third equation alone. And I'm going to add those together. So my x's get eliminated. I end up with 9y plus 18z is equal to negative 15. All right, so now I'm going to take these two equations. I have A, I have B, and I'm going to multiply them. Let's see what I want to get rid of. I think I'm going to get rid of the y's. So if I start with equation A and B, and I want to get rid of the y's, I'm going to use the multiple 6 and 9 to get 18. So I'm going to multiply the first equation by negative 3, giving me a negative 18y minus 36z equals negative 9. I'm going to multiply the second equation by 2, so this time I had to multiply both. That's going to give me 18y plus 36z equals negative 30. And when I add these together, I end up getting 0 is equal to negative 39. Well, that can't be equal. So what's happening here is I'm getting two planes not intersecting at all. So that's going to give me a no solution. Now, I would encourage you, if you get a no solution like that, to go back and make sure you didn't make any mistakes. But as soon as you get 0 is equal to a value that's not 0, you can assume that's a no solution. All right, so we're going to move on to our last example. Our last example is a word problem. So for that reason, we're going to have to take what's in this problem and we're going to have to write our equations out. All right, so in this problem, we're looking at a sports stadium that has 49,000 total seats altogether. Some of those seats are at the upper level, some are at the middle level, and some are at the bottom level. And you can see that the price for each of those levels are different. So those are going to be my variables because it says at the end, when all of the seats are sold for an event and the total revenue is $1,419,500, how many seats are there in each level? So we're looking for how many are in the bottom level, how many are in the middle level, and how many are in the top level or the upper up level. All right, so now I need to build my equations. So it says there are a total of 49,000 seats. That means regardless of where they are, the bottom plus the middle plus the upper is equal to 49,000. Now, the price for each are 35 at the bottom level, 30 at the middle level, and 25 at the upper level for a total revenue of $1,419,500. So there's our first two equations. Remembering when I have three unknowns, I need a third equation. So the third equation is going to come from this sentence right here. It says the number of seats in the middle and the bottom levels together equals the number of seats in the upper level. Okay, so middle and bottom together make upper. So that's going to look like this. Bottom plus middle is equal to upper. And that gives me my third equation. Now, if I look at these, I can see not all three equations are lined up. So I can either choose to line them all up in standard form and solve like I've done the previous, or because this one is already solved for you, what I can do here is use substitution. So if I know that u is equal to b plus m, I could put that b plus m into both of these equations, and then I have two equations with only two unknowns. So I'm going to go that route in this problem. So I'm going to make my first equation be b plus m plus, and instead of this u, I'm going to replace it with b plus m to give me 49,000. All right, if I simplify that out, that's going to be 2b plus 2m is equal to 49,000. There's my first equation. I'm going to do the same thing in the second one. I'm going to replace this u with b plus m. So that's going to give me 35b plus 30m plus 25 times b plus m. So that means I'm going to have 25 b's and 25 m's to total 1,419,500. So I'm going to distribute that 25 and then collect my like terms. So if I have 25 b's here and 35 b's here, I have 60 b's altogether. I have 25 m's and 30 m's give me 55 m's for the total of 1,419,500. And this gives me equation 2. So these are my two equations I'm working with, equation 1 and equation 2. Now I'm going to take a look at those and I'm going to decide, do I want to eliminate b or m? It looks like it's going to be easier for me to do b so I don't have to work with fractions or decimals. So I'm going to take equation 1 and I'm going to multiply equation 1 times negative 30. So that's going to give me negative 60b minus 60m equals negative, if I take negative 30 times 49,000, I get negative 1,470,000. I'm going to leave equation 2 exactly like it is. We're almost there. I know it seems like we're so far away. We're going to cancel those b's. I'm left with negative 5m equals negative 50,500. And when I divide by negative 5, I get the number of middle seats is equal to 10,100. All right, now what I'm going to do is I'm going to take either an equation 1 or equation 2. I'm going to replace that m with 10,100. And when I solve for b in equation 1, I'm going to end up with 14,400 seats. And over here it says, well, b plus m is equal to u. So if I add those two together, my u is going to end up being 24,500 seats. So this is middle seats, and this is bottom seats, and this is upper seats. All right, so this concludes our lesson on systems of equations with 3 variables. I'm going to go ahead and post your assignment to Google Classroom. Go ahead and try a couple problems on your own this evening, and we'll talk about them tomorrow. I hope you have a great day.